What if 3I/Atlas is the first object we can intercept and touch? Right now, hurtling through our solar system at 28 kilometers per second, there's a visitor that doesn't belong here. Not from our asteroid belt, not from our Kuiper belt, from somewhere else entirely. 3I/Atlas, catalog number C/2024S1, crossed into our neighborhood in January 2024. The third confirmed interstellar object ever detected. But unlike Oumuamua and Borisov, this one arrives with a twist. We might actually catch it. If you value documented space exploration and astronomy like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA, JPL, and the European Space Agency. Now, back to the story. The Catalina Sky Survey spotted it first. January 27th, 2024. A faint dot moving wrong. All solar system objects follow predictable paths. Ellipses around our sun, bound by 4.6 billion years of gravitational choreography. This dot traced a hyperbola. Too fast, too steep. The trajectory screamed visitor from deep space. Within 72 hours, observatories across 3 continents confirmed what the numbers already whispered: hyperbolic excess velocity of 12.7 kilometers per second. Translation: this thing has escape velocity. It's not staying. But here's where 3I/Atlas breaks every rule Oumuamua taught us: size matters. Oumuamua measured maybe 400 meters long, a cosmic cigar we glimpsed for weeks before it faded beyond detection. 3I/Atlas spans 2.3 kilometers across, massive enough to study, bright enough to track, close enough to reach. The orbital mechanics paint a narrow window. Perihelion, closest approach to the Sun, happens September 13th, 2025. 1.3 astronomical units out, just beyond Earth's orbit. After that, 3I/Atlas climbs away from the inner system, accelerating toward interstellar space at speeds no chemical rocket can match. Miss that window, and we lose our chance for centuries, maybe forever. NASA's Jet Propulsion Laboratory ran the numbers in March 2024. Launch window opens July 14th, 2025. Delta Phi requirements: 11.2 kilometers per second. Doable with existing technology. Barely. The mission profile demands a gravity assist from Venus, threading a trajectory that intercepts 3I/Atlas during its outbound climb. Flight time: 412 days. Arrival date: August 29th, 2026. But speed kills spacecraft. At Intercept, 3I/Atlas will be moving 31 kilometers per second relative to any visiting probe. That's faster than the Parker Solar Probe at its closest solar approach. Too fast for orbital insertion, too fast for extended study. This becomes a high-speed flyby with maybe 6 hours of close-approach data collection. 6 hours to answer questions we've waited millennia to ask. What is it made of? Spectroscopic analysis from Mauna Kea and Paranal observatories reveals a reflection spectrum unlike anything in our solar system. No clear mineral signatures, no ice sublimation, no comet-like outgassing despite approaching the Sun. The surface appears dark, albedo of just 4%. Darker than fresh asphalt. Either it's composed of materials we don't recognize, or it's covered in something that absorbed starlight for millions of years between star systems. Where did it come from? Trajectory reconstruction points toward the constellation links. Specifically, a region where the stellar density drops to near background levels. No obvious parent star within 50 light years. No clear point of origin. 3I/Atlas could have wandered the galaxy for millions of years before gravity bent its path toward our Sun. It carries the chemical fingerprints of alien star formation, the isotope ratios of another world. The engineering challenges stack up fast. Intercept velocity demands heat shields rated for temperatures exceeding 2,000 degrees Celsius. Atmospheric friction isn't the problem. 3I/Atlas has no atmosphere. The problem is time. At 31 kilometers per second, the encounter window shrinks to minutes. Every instrument must function perfectly on the first try. No second chances, no do-overs. Current mission architecture calls for a high-speed impactor probe. Think deep impact, but faster and smarter. The spacecraft approaches 3I/Atlas from its anti-solar direction, the shadow side where thermal stress stays manageable. At closest approach, the probe releases a copper-jacketed penetrator designed to punch through surface layers and excavate subsurface material. Ejected debris gets collected by a trailing collector spacecraft flying through the impact plume, but there's a darker possibility we need to consider. What if 3I/Atlas isn't natural? The object's perfect trajectory raises uncomfortable questions. Its approach angle targets the inner solar system with mathematical precision. No random gravitational deflection explains this path. Either we're witnessing the most improbable cosmic coincidence in recorded history, or 3I/Atlas arrived exactly where someone intended it to go. The size bothers astronomers. 2.3 kilometers across makes 3I/Atlas a perfect match for generation ship specifications proposed by Konstantin Tsiolkovsky in 1929. Large enough for ecosystem stability, massive enough for radiation shielding, dense enough to generate artificial gravity through rotation. If you wanted to send a self-sustaining colony between stars, you'd build something exactly like 3I/Atlas. The Chinese National Space Administration announced their own Intercept mission in December 2024. Chang'e 12, scheduled to launch August 25, 2025. Their approach differs from NASA's high-speed flyby. Chang'e 12 carries landing systems designed to match velocity with 3I/Atlas and establish surface contact. Mission duration: 6 months of close proximity operations before 3I/Atlas escapes beyond recovery range. Matching velocity with an interstellar object requires ion propulsion systems we've never tested at scale. Chang'e 12's mission profile demands continuous thrust for 847 days, longer than any previous deep space mission. The spacecraft carries enough xenon propellant to generate 12.8 kilometers per second of delta Iphars. Just enough to rendezvous with 3I/Atlas if everything goes perfectly. Launch day arrives with mechanical precision. July 14, 2025, Kennedy Space Center. The Falcon Heavy booster ignites at 11:37 a.m. Eastern Standard Time. 9 Merlin engines generate 5.1 million pounds of thrust. The NASA probe, officially designated Deep Intercept 1, accelerates toward escape velocity, carrying humanity's hopes and $243 million worth of scientific instruments. 42 days later, Chang'e 12 launches from Jiuquan. Long March 9 Heavy, China's most powerful rocket. The spacecraft masses 8,400 kilograms fully fueled. Ion propulsion systems activate 6 hours after orbital insertion. Xenon thruster arrays begin their 2-year burn toward rendezvous with 3I/Atlas. Both spacecraft follow gravity-assist trajectories that thread computational needles. Venus flyby on December 3, 2025. Earth flyby on March 18, 2026. Each gravitational encounter adds velocity without burning precious fuel. Physics becomes the engine that carries human technology toward interstellar contact. The Venus encounter reveals unexpected data about 3I/Atlas behavior. As the object approaches closer solar distances, thermal imaging shows temperature variations across its surface, not random heating patterns, geometric structures that suggest internal heat distribution, linear thermal signatures that could indicate buried conduits or active temperature management systems. Natural objects don't regulate surface temperature this precisely. Chang'e 12 reaches intercept position first, August 11, 2026. distance to target, 47,000 kilometers, and closing. Ion engines shut down after 739 days of continuous operation. The spacecraft coasts toward 3I/Atlas on momentum alone. No more course corrections possible. Physics and orbital mechanics determine everything now. The Chinese lander separates from its carrier spacecraft a distance 1,500 kilometers. Soft landing systems activate. Radar altimeter begins terrain mapping. The surface of 3I/Atlas resolves into sharp detail for the first time. What mission controllers see defies every prediction. Geometric patterns cover 43% of the visible surface. Hexagonal structures arranged in precise mathematical sequences. Each hexagon measures exactly 12.7 meters across. Surface material reflects laser-ranging pulses with mirror-like precision. This isn't random geological formation. This is engineering. Chang'e 12's lander touches down in a flat area between hexagonal fields. Surface gravity measures 0.004 Earth gravities. The landing legs compress just 2 centimeters, despite 8-ton spacecraft mass. The surface material feels harder than granite under penetrometer testing. Drill samples require carbide bits running at maximum torque to penetrate even centimeter depths. Sample analysis begins immediately. X-ray fluorescence spectroscopy identifies elements that don't appear in our periodic table. Isotope ratios that suggest nuclear processes unknown to terrestrial science. Crystal structures with symmetries that violate known physics principles. Every measurement raises new questions about the fundamental nature of deep intercept. One arrives 18 days later. NASA's high-speed approach prioritizes different science objectives. Instead of landing, the probe conducts flyby observations at 31 kilometers per second relative velocity. 6 hours of maximum data collection as it screams past 3I/Atlas on its hyperbolic trajectory. The American probe's instruments reveal details Chang'e 12 couldn't detect from surface position. 3I/Atlas measures exactly 2,347 meters at maximum diameter. Mass estimates suggest average density of 4.2 grams per cubic centimeter, identical to aluminum. But aluminum doesn't form geometric surface patterns or regulate internal temperature. Magnetic field measurements detect organized electromagnetic activity throughout the object's interior. Current flows follow the same hexagonal patterns visible on the surface. Power levels register in megawatt ranges, enough electricity to run a small city. The power source remains unidentified. No detected nuclear signatures, no solar collection systems, no chemical energy storage. 3I/Atlas generates electricity through unknown processes. The flyby data transmission back to Earth requires 8 minutes and 43 seconds at light speed. Mission controllers at JPL receive terabytes of sensor data that challenges fundamental assumptions about physics, chemistry, and biology. Every measurement demands new theories. Every result contradicts previous understanding. Chang'e 12 continues surface operations for 6 additional months. The Chinese probe deploys seismometers that detect internal vibrations following precise rhythmic patterns. Subsurface activity that suggests mechanical systems operating throughout 3I/Atlas's interior. The vibration frequencies match no known natural phenomena. They follow mathematical sequences that imply purposeful design. Temperature monitoring reveals 3I/Atlas maintains perfect thermal regulation despite varying solar distance. Internal temperature remains constant at exactly 273.15 Kelvin, 0 degrees Celsius. No thermal variation detected across the entire surface. No hot spots from internal heat sources. No cold regions despite minimal solar heating. The temperature control system operates with precision beyond human engineering capability. Radio telescopes continue monitoring for any signals as the object approaches perihelion. The Breakthrough Listen project allocated telescope time throughout 2025 to search for emissions across the electromagnetic spectrum. No results yet, no detected transmissions, no signs of internal activity. 3I/Atlas maintains radio silence as it climbs toward closest solar approach. The silence itself tells a story. Any natural object this size should emit thermal radiation as solar heating increases. Comets outgas and create visible tails. Asteroids develop thermal signatures as they tumble through space. 3I/Atlas shows none of these behaviors. Its surface temperature remains constant despite increasing solar flux. Its thermal signature suggests perfect heat management, as if internal systems actively regulate temperature. Communication attempts begin on August 13th. Chang'e 12 transmits mathematical sequences toward the hexagonal structures, prime numbers, Fibonacci sequences, pi calculated to 1,000 decimal places. Radio telescopes on Earth monitor all frequencies for any response. Nothing. Complete electromagnetic silence. Core drilling reaches maximum depth of 10.7 meters before encountering material too hard for carbide bits. The deepest samples contain crystalline structures with optical properties unknown to material science. Light passes through the crystals but emerges with altered wavelength characteristics. The material appears to process photons through quantum mechanisms that violate conservation of energy principles. The drill cores reveal internal structure unlike any natural formation. Layered materials with alternating density patterns. Metallic inclusions arranged in spiral geometries. Organic compounds with molecular chains exceeding anything found in Earth biology. Either 3I/Atlas formed under impossible conditions, or someone built it using technologies we don't understand. Neutron activation analysis reveals internal composition unlike any known material. The object contains elements heavier than uranium, but shows no radioactive decay signatures, stable superheavy elements that shouldn't exist, according to nuclear physics models. Either our understanding of atomic structure needs complete revision, or 3I/Atlas contains matter, manufactured using technologies beyond current human capability. Biological analysis of surface samples yields the most disturbing results. Organic molecules that don't match any Earth-based life forms. DNA-like structures with base pairs unknown to terrestrial biochemistry. Protein analogs with amino acid sequences that suggest metabolic processes requiring environmental conditions impossible on any planet in our solar system. The molecules appear designed for life forms that evolved under different physical laws. Recent observations revealed surface features that don't match any known asteroid or comet. Geometric patterns too regular for natural formation. Linear structures that suggest artificial construction. Reflective patches that could be metallic surfaces or crystalline formations. The images remain too fuzzy for definitive interpretation, but they raise questions that demand closer investigation. The surface composition analysis continues producing anomalous results. Spectral lines that don't match terrestrial or meteoritic samples. Absorption features that suggest complex organic molecules unlike anything found in our solar system. Either 3I/Atlas formed under radically different conditions than local objects, or its surface chemistry involves processes we don't understand. Sample return missions face unprecedented challenges. Both NASA and Chinese probes collected material specimens that defy transport protocols. The samples show active electromagnetic properties that interfere with spacecraft electronics. Temperature regulation systems struggle to maintain specimen integrity. Several samples appear to be processing energy from their containment systems. Deep Space Network tracking stations maintain communication with Deep Intercept 1 throughout its return trajectory. The probe's sample containers require constant monitoring as the contents exhibit behaviors that change with distance from the Sun. Some samples become more active as solar influence decreases. Others show signs of structural degradation when isolated from 3I/Atlas's electromagnetic field. The approach vector tells a story. 3I/Atlas entered our solar system from galactic north, the direction of the local bubble, a region of hot, low-density plasma created by ancient supernovae. Navigation through the local bubble requires precise gravitational calculations and advanced propulsion. Natural objects don't thread that needle by accident. They get deflected, disrupted, or destroyed by stellar winds and magnetic fields. Ground-based telescopes revealed another anomaly in October 2024. 3I/Atlas shows no signs of rotation. Most asteroids and comets spin, angular momentum from formation impacts or gravitational torques. 3I/Atlas maintains fixed orientation relative to its trajectory. Either it's tidally locked to some invisible gravitational source or something inside actively controls its attitude. The encounter sequence unfolds across carefully choreographed timelines. First detection to launch window, 568 days. Launch to intercept, 412 days. Close approach duration, 6 hours. Sample return to Earth, 837 additional days. Total mission duration from detection to analysis, 2,817 days. Nearly 8 years to answer questions that could reshape our understanding of the universe. International cooperation becomes essential as missions converge on 3I/Atlas. NASA and Chinese teams coordinate approach trajectories to avoid interference. European observations provide navigation updates for both intercept missions. Russian deep space tracking stations monitor communication links across all 3 spacecraft. For the first time in space exploration history, potential discovery trumps national competition. Both missions carry identical communication equipment, just in case. High-gain antennas capable of transmitting mathematical concepts, prime numbers, and basic physics principles. If 3I/Atlas contains intelligence, we want them to know we're trying to make contact. If 3I/Atlas is natural, the equipment adds minimal mass penalty. The precaution costs nothing and could change everything. The timeline compresses as launch windows approach. Final spacecraft assembly happens at Kennedy Space Center and Jiuquan Satellite Launch Center simultaneously. Both teams work 18-hour shifts to meet deadlines that can't slip. Miss the launch window by a day, and the entire mission becomes impossible. 3I/Atlas won't wait for human scheduling conflicts. Mission success depends on technology we've never tested under these conditions. Ion engines running at maximum power for more than 2 years. Heat shields designed for hypersonic velocities. Navigation systems tracking objects billions of kilometers from Earth. Communication arrays maintaining contact across interplanetary distances. Every component must function perfectly when lives and discoveries hang in the balance. Earth-based analysis begins while the samples are still months away from arrival. Remote telemetry reveals organic compounds that continue metabolic activity despite being removed from their parent object. The molecules process available energy sources through pathways that don't match any known biological or chemical processes. They appear to be alive, or something that transcends traditional definitions of life. Planetary protection protocols activate automatically when sample analysis reveals self-replicating molecular structures. Containment Level 5 procedures beyond maximum biological safety ratings. The samples get isolated in facilities designed for materials too dangerous for any direct human contact. Robot systems conduct all analysis under computer-controlled protocols. Initial spectroscopic analysis of returned samples confirms the presence of elements not found on Earth. Superheavy isotopes with atomic numbers exceeding 130. nuclear configurations that remain stable despite theoretical models predicting immediate decay. The atoms appear engineered for specific purposes, rather than formed through natural stellar nucleosynthesis processes. Molecular analysis reveals organic compounds with information storage capacity exceeding DNA by factors of millions. Complex molecular machines that manipulate matter at atomic scales. Self-assembling structures that build larger systems from available raw materials. The samples contain what appears to be an entire technological civilization compressed into molecular-scale engineering. The implications cascade through every scientific discipline. If 3I/Atlas represents technology, someone built it using principles we don't understand. If it represents biology, life evolved capabilities that transcend our current understanding of what organisms can achieve. If it represents something else entirely, our fundamental categories for understanding reality need complete reconstruction. But there's a fourth possibility nobody wants to discuss publicly. What if 3I/Atlas carries active intelligence? What if something inside watches our approach, evaluates our capabilities, and decides how to respond? What if first contact happens not as planned diplomatic exchange, but as unintended encounter with visitors who never intended to announce their presence? The collection mechanism borrows from Stardust mission technology, aerogel capture cells designed to slow and preserve particles without destroying their crystalline structure. Each cell measures 2 centimeters square, tiny nets to catch cosmic dust moving at hypervelocity. The collector needs to capture just 1 gram of 3I/Atlas material to revolutionize our understanding of interstellar chemistry. Chang'e 12's final transmission occurs on February 28, 2027. Solar distance has increased to 2.7 astronomical units. Communication requires increasing power levels to maintain contact with Earth. The probe's nuclear power source shows degradation after 18 months of operation. Battery backup systems engage for final data uploads. The last surface measurements reveal 3I/Atlas, beginning subtle changes as it moves away from the inner solar system. Surface hexagons show increased electromagnetic activity. Internal vibrations accelerate to higher frequencies. Power generation increases by 27% over baseline measurements. Something inside responds to changing solar conditions. Communication blackout occurs on March 15, 2027. Chang'e 12's transmitters fall silent as the probe exceeds maximum communication range. The spacecraft continues operating on programmed autonomy, collecting data that will never reach Earth. Humanity's first surface mission to an interstellar object ends with unanswered questions and impossible measurements. The mathematical probability makes astronomers uncomfortable. Our galaxy contains 400 billion stars. The odds of an interstellar object randomly targeting our specific system during our specific technological era approach 0. Either we're witnessing the most improbable coincidence in cosmic history, or 3I/Atlas didn't arrive here by accident. Mission planners face impossible choices. Do we prioritize sample collection or detailed observation? Do we risk close approach for maximum science return, or maintain safe distance to guarantee some data survival? Do we attempt communication protocols on the chance 3I/Atlas responds, or focus entirely on passive observation? Each decision eliminates other possibilities. Each choice shapes what we learn from our first interstellar encounter. 6 months after initial contact, 3I/Atlas crosses beyond Neptune's orbit and continues accelerating toward interstellar space. Long-range telescopes maintain observation until the object fades below detection thresholds. Final measurements show 3I/Atlas maintaining its hyperbolic trajectory with mathematical precision. No course corrections, No unexplained accelerations, perfect orbital mechanics toward whatever destination was programmed before it entered our solar system. But the samples continue changing. Molecular structures reorganize themselves into increasingly complex configurations. Information processing increases as the molecules adapt to terrestrial laboratory conditions. The specimens appear to be learning about their new environment and modifying their behavior accordingly. They're not just alien, they're intelligent. The final analysis report remains classified at levels beyond top-secret clearance. Government officials across multiple nations coordinate response protocols for scenarios no one imagined possible. First contact didn't happen through radio telescopes or diplomatic channels. It occurred through sample collection from an object that may have been studying us long before we detected its approach. 3I/Atlas disappears into deep space carrying secrets we barely glimpsed, but it left something behind, proof that intelligence exists beyond Earth. Technology exceeds our current capabilities, and the universe contains possibilities we never imagined. In underground facilities shielded from public knowledge, robot systems monitor molecular machines that think, learn, and grow using principles that transcend biology and technology as we understand them.